Have you ever wondered how a hot air balloon manages to stay afloat? Or how about the mysterious balance of liquids in a U-tube? Well, these are just a few examples of the fascinating world of fluid mechanics. Today, we are going to dive into these questions and more. First, consider a hot air balloon with a volume of 500 cubic meters and a mass of 100 kilograms. The air surrounding the balloon has a density of 1.2 kilograms per cubic meter. How much buoyant force does the balloon experience? The answer lies in the principle of buoyancy, which states that the buoyant force experienced by an object is equal to the weight of the fluid displaced by the object. By applying the formula for buoyancy, which is the product of the fluid's density, gravitational acceleration, and the volume of the fluid displaced, we find that the buoyant force experienced by the balloon is 5,880 newtons. This tells us that buoyancy is a force that opposes the weight of an object submerged in a fluid. It is proportional to the fluid's density, gravitational acceleration, and the volume of the fluid displaced. The greater any of these factors, the greater the buoyant force experienced by the object. Now let's shift gears and look at a U-tube containing water and oil with a density of 800 kilograms per cubic meter. If the water's height in one arm of the tube is 20 centimeters, what is the height of the oil in the other arm? The answer to this question comes from the principle of hydrostatic pressure, which states that the pressure at a certain depth in a fluid is equal to the product of the fluid's density, gravitational acceleration, and the depth of the fluid. If we assume that the water and oil surfaces are level with the tube's surface, then the hydrostatic pressures in both arms of the tube must be the same. By equating the formulas for hydrostatic pressure in both arms of the tube and simplifying, we can find the oil's height. Knowing that the water's density is 1,000 kilograms per cubic meter and the water's height is 20 centimeters, we can calculate that the oil's height is 16 centimeters. This demonstrates that hydrostatic pressure is the pressure exerted by the weight of a fluid. It is proportional to the fluid's density, gravitational acceleration, and depth. The greater any of these factors, the greater the hydrostatic pressure experienced by the fluid. In a U-tube containing two different fluids, the hydrostatic pressures in both arms must be the same to prevent the fluids from moving. Therefore, we can balance the hydrostatic pressures in both arms to find the unknown fluid's height. So in this discussion, we've learned about the principles of buoyancy and hydrostatic pressure, and how they govern the behavior of fluids in various scenarios. We've seen how these principles can be applied to solve problems in fluid mechanics, from understanding the flight of hot air balloons to predicting the balance of liquids in a U-tube. Hopefully this gives you a deeper appreciation for the fascinating world of fluid mechanics.